Hello and welcome to the second session of our workshop series Engineering Simulation for Rhino Users, presented by McNeel Europe and SimScale. Yes, again, we are very happy to see so many people who have joined for our today's webinar. And actually, before we start to dive into the world of finite element analysis and structural simulation, I would like to make sure that everybody can hear us loud and clearly. And we are using a software called GoToWebinar to deliver this live session. And right now you will find the GoToWebinar control panel on your desktop, and there is a button called Raise My Hand. And please click on the Raise My Hand button in the case you can hear me loud and clearly. Yes, I see some hands. Seems like everything is working. However, we also provide as an alternative a toll-free audio service number, which you can call to follow the voice of the presenters. Therefore, you just have to choose one of this bunch of toll-free numbers, and we are providing different numbers for a lot of countries. And please dial into your phone once you're asked following access code 192903379. Great. Good to know that the technical stuff is working properly. And let's now take a look at our today's agenda. And as you know, this workshop series is a joint initiative between or with SimScale and McNeel Europe. And our aim is to show Rhino users how they can use engineering simulation to create and deliver better products in a short time. And therefore, this webinar is basically made of three sections. At the very beginning, during the first part, we will talk a little bit about the fundamentals of engineering simulation and especially finite element analysis. So we will talk about the advantages and limitations of engineering simulation, about the possibilities and the range of application you can use solid mechanics simulation for, and we will also introduce you to the SimScale cloud-based simulation platform. At the second part of the session, we will do a hands-on live demo, where Rodrigo from McNeel will show you how to prepare a Rhino model properly for simulation. I will show you how to quickly set up structural mechanics simulation of a chair within 5 minutes. And at the final part, we will discuss two case studies we've prepared, which show how our customers are leveraging simulation to improve their products. And finally, we will have time for Q&A. So let's start and talk a little bit about the fundamentals. Just one thing, in the case you have questions, especially related to the fundamentals or to some else part of this presentation, please write your question in our question box, and I will try to answer the question during my presentation or at least during the Q&A. But now let's start. And maybe the first thing you noticed is that basically there are two words used for solid mechanics simulation. One is finite element analysis, FEA, and another one is just solid simulation or structural simulation. Basically, they mean the same. And FEA is about performing mechanical experiments virtually on your computer. And in the end of the day, FEA allows you to run a virtual lab where you can test the mechanical behavior of your products without manufacturing them. And on the slide, you can just see some example which show the high bandwidth of applications you can use a finite element analysis for. For example, here in the middle, you see a visualization of a stress simulation inside the global valve. And these kinds of valves are used, for example, in large plants or factories to steer other components, and therefore designing them can be very challenging because on the one hand you want to make them as cheap and light as possible and reduce the pressure drop inside these valves. On the other hand, you want to make sure it's robust enough. And this is a very good example. And with the help of the simulation of FEA, you can really dive into your part and find out about all the stresses, strains, and displacement happening inside the structure for every given time. Another very good example is this one here. Here you can actually see two skull bones, and here we simulated the impact of wearing a helmet during a crash with a bike, for example. And the colors are again representing the stress. And here you can clearly see like how the overall stress is limited when using a helmet. And this is another good example for FEA. But FEA is not only limited to structural deformations, it can also be applied on thermal problems. For example, here, this is the stress induced by heat transfer inside the pipe, and here you can actually predict where, if yes, where this pipe can crack. Or again, something completely different. What you can see here is a simulation of a manufacturing process, and it's about calculating like deformations and stresses during hollowing a pipe. All right, so, and I think now you actually know what FEA is, but let's talk about the potentials of finite element analyzers and what are the reasons why companies are using it. And therefore, I would like to talk with you about the general way products are developed. And this is a chart I like very much because basically you can use it independent from the industry. And this one is basically comparing like the project costs over how project costs are planned and in the end realized during different stages of product development process. And let's think about it. When you start to design a product and it really does not make a difference which kind of product. At the very beginning, you're basically defining most of the costs up front. And here we do a lot of assumptions and guesses. And in the end of the day, at the beginning, you have to think about like, what is the final aim of my product? What are the criteria it should fulfill? And you also try to plan this process. And in the end of the day, before you start to develop a process, you try to gather as many information as possible to make sure this project will be successful. So what I want to say is, in the end of the day, most of decisions for a product development project are taken basically before you start with this development project. Now, on the other hand, if you take a look at the costs, only a fraction of the cost is basically generated during the realization of this plan, and because at the beginning you just have a concept, maybe 1 or 2 employees working on it, while at the end of the design process, much more people are involved and you need much more resources. And this is basically a tension field for every product designer or engineer. And this is, by the way, a very good example why simulation, or in particular finite elements analyzers, is so helpful, because it allows us at the very beginning of the product development process to compare, let's say, fundamental concepts, to validate, for example, assumptions, and in the end of the day, it allows us to create or to finish projects with lower costs at a shorter time. And in the end of the day, it allows us to create better products. And just think about it. For example, a very good example here is a car manufacturer. If you think about new cars, they are heavily tested to make sure that they are safe. And when you start to design a car, a lot of things are not clear. For example, the overall shape of the car, and a lot of details how the design should exactly look like. And instead of like building hundreds of different concepts and realizing them and doing a crash test, a physical crash test, which would be very expensive, they can start at the very beginning of the project to do some research with basic models. And in the end of the day, hundreds of thousands of car designs are tested virtually, but only a few ones in the end of the day needs to be validated with the experimental test, which helps to save a lot of money. And now let's talk about the last aspect of the fundamentals of finite element analysis. And basically, I know that it's not so important if you want to apply it maybe, but a lot of people ask us about the idea of finite element analysis and how it's actually working. So let's try to understand what is the philosophy between engineering simulation and in special structural simulation. So if we talk about physics really in a general way, independent if we're talking about flow, about solid mechanics, about thermodynamics, there are equations out there which are describing like what is happening in the nature. And these equations are very special kind of equations. It's not that kind of equation we learned at school, for example. They are so-called partial differential equation, which means they are not depending only on variables like, for example, position or time of your model, but also on derivatives, which means it's very complex to solve these equations and nearly impossible. So again, we have some good news for most of phenomena we're interested in, like stress distribution or heat distribution. We have equations which are describing these problems. But on the other hand, we are not able to solve these equations. But what we do in general, and if you followed our last session last week about computational fluid dynamics, I think you will see some things which are parallel. And when using FEA, what we basically do, we take these equations we cannot solve for a complex real-world problem, and instead of solving them analytically, we use discretized a function which gives us a kind of approximate solution. And this process is basically the key or the fundamental idea of finite element analysis, because it allows in the end to convert a very complex problem into a system of simpler problems, a system of linear equations, and in contrast to this partial differential equations we cannot solve. We can solve the linear equations very easily using large computers, because basically that is one of the biggest advantages of computers. They are very fast and effective in using linear equation systems. And I know that this was maybe very general, so let's try to make it a little bit more hands-on. So just imagine you are interested in the stress distribution inside this kind of hook. And in the end of the day, what you want to understand is, for a given load and a given geometry from a given material, what is the stress and the displacement of material inside this hook. And one way would be to take this partial differential equations, and if we would be able to solve them, what we are not, we would get back a kind of function which would give us stress, strain, displacement for every point. I mean, really, for this infinite number of points inside this model for every time step. And this is not possible, as I mentioned. So what do we do instead? We replace our model with a discretized model which is based on a finite number of degrees of freedoms, which means instead of considering or analyzing every point in the structure, we are just considering or just calculating what is happening at some defined points, our degrees of freedom. And this allows us to replace our complex problem with a system of let's say simple elements. And these elements here, you can see one is here, one is here. They are called finite elements, and you can imagine this as a small piece of structure. And in the end of the day, what we are doing is that we are only taking a look at what is happening at the nodes, and everything which is happening between these nodes is interpolated. And this allows us to calculate an approximate solution for, let's say, all kinds of structural problems using a computer. And let me give you a very simple example, and then we are done with the theoretical section. Just imagine this is a structure we want to investigate, just a metal beam. And when doing FEA, instead of considering the whole beam, we will just take, in this example, 2 points. That's basically the simplest FEA model possible. And if you take a look at this point, you can write down these equations. And if you had solid mechanics at school or at college, you are maybe familiar with that. If not, don't worry. The only thing you have to understand and remember is that what we can do now is to give relations between these points, and they are depending on the coordinate of the point, so of the displacement of each point, of the material properties of this bar, in this case the elasticity, the cross-section of this bar, and the length. And using these constitutive equations allows us to solve this equation, which means if we now have this model and you tell me I want to have the following load F2 on this side, and for example following load on this side, I can calculate everything else. And if you're interested on the fundamentals and the math, there's a very good video on YouTube where someone is explaining it very detailed. And usually we use our own materials or videos, but in this case I can really recommend this video. It's really nice. And just check this link and you will find it. And now, just to make this a little bit more vivid. So let's take the same example from, with the bar, just with maybe some more points. So, and the blue, in blue you can see the exact solution of this problem, and in red what FEA gives us. And basically we're just calculating now the displacement of this point in this direction depending on the x-coordinate here. Here you can see for FEA we're just calculating inside or for some defined points, and in between it's interpolated with a linear function. And that's basically a very essential challenge when running a simulation. In the end of the day, in advance, you should have a rough idea about how your physics are looking like, and you use more points and more small elements there where you expect to have large deformations, and where you expect to have very low or small deformations, you can lose less points. Okay, right. So let's take a look at our question box just to make sure everything is fine. So first question is by Pete, and Pete said he had to leave soon, and if we are offering also a recording. And yes, for sure. So we are recording this session, and we will send you tomorrow a link with the recording to this session. So in the case you want to take rewatch this webinar, don't worry, it will be possible. Right, and now let's take a look at SimScale. So I don't want to talk so much about us as a company, maybe just some facts for you. We are founded 4 years ago as a spin-off of Technical University Munich, and back then the idea was to enable every engineer and designer in the world to use simulation. And let's take a look how simulation is adapted today in industry. And on this chart on the left side, you can basically see how different kind of software technology were adopted in industry over time. And on the x-axis, we have time from the 1970s until today, and on the y-axis, we have the adoption in the industry in percent. And if you take a look at 2D CAD, it was developed in the 70s and adapted within 20 years completely in the industry. And also in parallel with like 10 years later or 7 years later start, the same for 3D CAD. And here what you can basically see is what happened is technology was invented, for example 2D CAD in the 70s, and then some major technological changes enabled majority of engineers and designers to adapt the technology. For example, at 2D CAD, it was availability of CAD on personal computers, and the same with 3D CAD. If you take a look at simulation, it was basically invented in the same year like 2D CAD, but still the adoption rate is much lower. And today, around 4% of engineers and designers have access to simulation tools, which is quite low. And you ask yourself, okay, what's the reason? Basically, there are 3 reasons. The first reason is what we call the access barrier. In contrast to hands-on CAD tools like Rhino, which you can download directly, install and use, simulation tools usually come with a much more complex installation and buying process. So you need to install a license manager, you need to set up a HPC infrastructure for scheduling the simulation jobs, you need to install software licenses, which is much more complex, and so on. And this is, by the way, very much associated with the so-called budget barrier, which means simulation tools are very expensive so far, and you have to invest really a high amount of money for buying the hardware, for buying software licenses and training. And usually you are like spending 30 to 40k euros upfront just to buying the infrastructure, which is for sure a killer for small companies. And another thing, and which may be the most important thing, so-called know-how barrier. Most of the simulation tools were really designed and built for specialists, which are very experienced with theoretical mathematics, numerics, and engineering theory in general, and they require a lot of specific know-how and experience. And when this company was founded, the idea was, what can we do to solve this problem and make simulation accessible to every designer in the world? And that was when SimScale was born, the first cloud-based simulation platform and ecosystem. So to put it in a nutshell, SimScale is the very first 100% cloud-based simulation platform running in your web browser, which means you don't need to buy any dedicated hardware to install software or licenses. The only thing you need to access unlimited simulation power is a web browser, a standard web browser, and a working internet connection. And everything else will be performed in the cloud. And together with this new technology, we also developed a completely new price model, which is based on a service as a service approach, which means you're not anymore buying software licenses, but you are paying as you go for the simulations you want to perform. And therefore, this allows companies independent from the size to scale simulation based on the needs and the product development processes. And a very special thing about our price model is a so-called freemium approach, which means that as long as you use SimScale for, let's say, non-commercial projects and you're willing to share your simulations with other users, you can use SimScale completely for free. And for sure, for commercial customers which want to keep the knowledge and don't share the stuff with others, we also provide customized commercial plans. And last but not least, SimScale is designed for everyone. And if you remember the last slide, I was also talking about the know-how barrier. And here I think we really found a good way to solve this problem. So SimScale was developed for designers and engineers who want to apply it and who are not experts in simulation in general. And we also have unique ways for documentation, collaboration, and working together, like our SimScale community, which is a community of hundreds of thousands of engineers and designers using SimScale, and where you will instantly find help to get started. And yes, let's just take a look about, on what SimScale is able to do. So first of all, it's a simulation platform which is not limited only to a single type of physics. And here you can see 4 very good examples showing the big bandwidth of simulation applications you can perform with SimScale. Starting from what we're talking about today, finite element analysis for solid mechanics simulation. Here, for example, you can see stress analysis of a wishbone suspension of a car. Or we could also support CFD, which is computational fluid dynamics. If you're interested in that, you should take a look at the recording from last week. And with CFD, you can basically simulate the behavior of fluid flows. And this is a very good example. So here we are calculating hydrodynamics plus aerodynamics of a ship hull, which is swimming through a river. Another kind of physics which is heavily used by our users is thermodynamics or thermal simulation, and this has also a very big range of applications. So basically, using this kind of simulation, you can simulate every phenomena where heat distribution is included. For example, the simulation of data center cooling. And this kind of simulation can be used to optimize the air conditioning layout for the racks. And we also support particle phenomena simulations, for example, bulk material transport inside a mill. And if we want to talk about finite element analysis or structural simulation, there's also a very high bandwidth of possible applications. For example, we support static stress simulation transient or dynamic simulations. For example, if you want to simulate dropping of a cell phone case, we also support thermal stress, which means stresses which are induced by heat transfer inside the solid material, and also, which is interesting everywhere, you have vibrations, harmonic simulations, and frequency analysis. All right, so let's now get hands-on and do our today's live demo. And first of all, let's talk about what we want to do today. So I talked to Rodrigo and he told me that a very common use case for Rhino users is product or consumer product design. And today we want to show you how you can create within 5 minutes a structural simulation of a chair. And what we have to do therefore is first of all to prepare the geometry, our CAD model for simulation. And this is what Roddy will show you in a couple of minutes, and how to prepare your simulation or your geometry for a simulation in Rhino. Then I will show you how to set up the simulation, which means create the mesh, so divide this model into the small finite elements, how to set up the simulation, analyze the results. Okay, so now I would like to give the word to Roddy. Roddy, can you hear me?
I can hear you okay, Milad, and well, thanks for the introduction and for the presentation until now, and of course for inviting us. Can you hear me okay?
Yes, it's. Can you maybe make it a little bit louder? Sound is a little bit
sure.
low.
Maybe a little better now. It's
yeah,
the
I just
okay,
made you the presenter.
Okay, great, excellent. There you go. Can you see my screen now?
Yeah, we can see your screen.
Okay, great, excellent. So, well, thanks for the invitation. Okay, and thanks everyone for the interest, all the attendees until now. Okay, so as Milad was saying, one of the cases, let's say, or case studies where Rhino could be used along with SimScale. Okay, would be analyzing the static stress analysis on a stool, right, or any kind of furniture item. Okay, as you all know, Rhino is widely used in the sector. Okay, so when Milad was asking me what kind of exercise could I prepare and so on, I just thought that maybe a simple stool where all the structural parts can actually be easily seen. Okay, would probably help make the point in the case. Okay, so I prepared 3 different examples, all of them very easy, let's say, quite simple, right? And then I prepared STP, a step file, right, to just re-import it into Rhino, and everything was being closed and able to be meshed on SimScale, right? And when I was just reloading the file today, I just realized that actually on the very last step of one of the exercises, I had left a mistake, right? This was unaverted, but actually when I reopened, I thought that this was actually an excellent case to just do this live, right, and fixing this problem live. Okay, so this was the file, as you can see here, almost complete when I was preparing it. Okay, it's a constant thickness shell, right, could be easily injected, I guess, right? There's a stiffener structure in the lower area, right, so fillets there, and apparently everything's almost finished. The only thing that we need to do probably would be joining everything together, because as you can see here, the outer and the inner shell are separate parts. Okay, so the first thing that I'm going to do is running select curve, cell CRV, to select all the curves and hide them, right, because I don't want to use them right now. And one of the first things that we should always do actually when doing this kind of let's say finishing operations is trying to join everything together. So I'm just going to run Windows Select and just grab everything together, use join to make sure that Rhino is selecting and joining as much geometry as possible. And as you can see here, Rhino has joined 10 different surfaces or polysurfaces into one single open polysurface. Okay, remember that whenever you want to know more details about an object, you can just go to the Properties tab here, click on the Object Properties, select Details, and there you go. Rhino will just tell you how many surfaces you are using on this polysurface, how many edges we have, and it looks like we have 16 boundary edges, that is outer naked edges, and 144 internal edges. Okay, right, this is quite interesting, but not very descriptive on the viewport itself. Okay, the command that I would like to introduce now is, where are you? Show edges. Here we go, because this command will let you know where are the actual open edges or naked edges, as we call them. Okay, as expected, we have 16 naked edges, and after running the command, we can click on the zoom button here, and Rhino will just highlight the 4x4 16 edges. Okay, that's fine, with this color that we have here. Okay, if we look into every particular case, you will see that it seems like there's like a surface that I didn't trim, okay, that I forgot to trim when I was extending or filling the rounding on the internal part of the shell, right? There you go. So this is going to be an excellent case to make my my point. Okay, right. The first thing that I'm going to do is actually extracting the upper surface here. This one. Well, sorry, because copy is set to yes, and actually I'm going to repeat, copy should be set to no, just to make sure that I'm not copying the. There you go. So I'm just going to extract this and maybe just hide them. There you go. So now I can see the interior part, let's say, of the poly surface, right? I can just now basically zoom in around here. Oops, sorry. Zoom in right here, and there you go. That's the surface that I have to trim actually. With duplicate edge, should be quite easy for me. Where are you, duplicate edge? To duplicate this edge here, that one here, there you go. And now use them as trimming objects to trim away that part or that part. Okay, actually be careful when you do this, because we should be exploding everything so that we can trim away only this bit of the offending surface, right? So these two, click on trim, off you go, off you go. Whenever you see this kind of, say, artifacts, okay, remember that most likely that has to do with the rendering mesh. Okay, so I'm just gonna set this to smooth and slower, click on preview, and there you go, off you go. You know that Rhino uses a preview mesh, a rendering mesh on top of the viewport. So whenever you see this kind of jagged edges, that's what we need to do, right? So I'm just gonna right click here to get to the last 20 commands that we use, duplicate again this edge, same thing here, use trim or split to get rid of that part, this one here, right, there you go, looks quite okay. And the same thing here. Of course, this is symmetric, and if I had realized that mistake before, I could have just do all these operations in one of the 4 quarts, okay, and then just mirror everything. But since everything's ready, probably it's going to be faster if I just do this live on the finished exercise. There you go. I'm going to select the, there you go, all the curves again, delete them because those were just auxiliary objects. See if I can join everything again. Again, this is an open pole surface, of course, because the top is missing there, right? What can I do to double check this? Select this, and as expected, the open area, let's say, still shows up as a naked edge, right? Another way of checking whenever an object is, say, showing some interior bits, okay, on the display viewport options, if you go to view, display modes, I'm using ghosted there, okay, right here, there's an option that will highlight back faces of a surface with a different color, okay, I'm just going to use then this color, and as you can see now, apparently one face of a surface is shown with a color and the other with a different color, okay? So this layer is set to use green as the main display color, and apparently the inside of the surface is shown as the back face, actually. This is because I guess that the whole surface is inside out. Okay, with analyze direction, we can double check that, and Rhino will just, there you go, you can see it here. We'll just show you which one is the positive side of the surface, and it looks like this surface is inside out. So I'm going to flip the whole surface. There you go. Now the positive side looks like the outer side, right? And we can see that the inner area is grayed out. Okay, so that trick, going to Tools, Options, Display, Tool, Options, Display, Options, back faces, okay, will let you highlight the back faces. Right, if I just right click here, then I will show all hidden objects. I can, with select curve, hide again all the curves and either delete them or hide them again. I don't really need them, okay? And the last surfaces that I created when I was extracting them. There you go. So not that one, but this one here, okay? I can try and join them together, reverse them also. Don't worry, because when joining objects, Rhino will just unify the normals, okay? But just for the sake of clarity, there you go. I can grab these two together, try to join them, and here's the magic word. I have joined everything into a closed polysurface, okay? Looks like I have some other items there. Don't worry, because I don't really need them. Those were just probably auxiliary surfaces, so I can hide all other layers. What other things to check? Well, as I just did before, I'm going to double check here, properties, details, and looks like this is a valid polysurface and it's actually closed. Okay, this is of utmost importance when you are exporting stuff from Rhino for this kind of operations, right? Another tool that we might want to use is the clipping plane. Okay, the clipping plane will let you apply a dynamic cut plane. There you go. Oops, sorry, because I should have activated this perspective viewport before calling clipping plane. There you go. Then do it here. There you go. So now I'm trimming away this viewport, okay, dynamically with this plane that I have defined, and I can move this, right? So this will let me check if there are actually any self-intersections or if we have a single clean wall in there. Okay, while this clipping plane is active, I can actually rotate it or do any kind of operation with it. So I can just rotate it away, place it here, see it from below, or turn it 180 degrees around so I can see, there you go, everything from there. And with the gimbal again active, should be quite easy for me to use, see if everything's, there you go, as expected here. Looks like so I think that, we can just carry on. Right, so another interesting tool that we could be mentioning now is the select bad objects. Okay, nothing gets selected, that's fine, that's good. That means that of the objects that I have on screen, nothing is highlighted as a bad object. Let me just go back to my OS partition here, because I wanted to show you a couple of articles on our wiki, okay, especially this one regarding fixing bad objects. A bad object is just some kind of object that violates any of the rules that actually are defined on the Rhino core. Okay, this means that there is actually something wrong with a surface or polysurface. Okay, it can be something really easy to fix or something quite complex. Okay, so take a look at this article. Right, if you just look for bad objects on our website, okay, you'll get to it, and yeah, this should help you identify, target, and fix all potential sources of errors. Okay, keep in mind also that we don't have solid objects per se in Rhino. Okay, we always deal with closed polysurfaces. So again, this other article called FAQ Closed Solids is quite interesting for anyone doing this kind of thing. Okay, something that I didn't mention at the beginning is that Rhino is quite a flexible tool in terms of opening, importing and exporting different file formats, okay? And here you have a complete takedown of all the file formats that we can manage, right? If I just go back here, right, before I export this, I'm just going to probably do a quick fillet here with fillet edge. So I'm going to grab this one, this one, this one here, that one here, this one there, just to clear a little bit and make our exercise here a little bit more interesting. So I'm going to activate the preview. Looks fine. 1 millimeter probably was quite low, but looks okay, right? And if you want, we can also just do a fast fillet on all the contour here. So again, this should be quite fast because I'm going to change the edges, okay? Set this to a tangency, there you go. Angle tolerance is 1. If I just click here, there you go. All the lower edge gets selected. That means that we do have continuity here, which is good, of course. Same thing here. Excellent. This was set to 1, so it might not work because I should have just set all. Actually, because if I'm using the same value, of course, this won't make any sense. So again, let me just go back, undo, repeat, set the radius to 0.75 to play it safe. Sorry, 0.75. Click on chain edges. Pick this one, pick that one. And there you go, everything gets selected now. And I think that we should be quite safe. Takes a few seconds to complete. And once that I'm cleared here, I think that we can just export as a step file. If I'm not wrong, SimScale, Milan, probably you can just confirm this or deny it. Rhino is able to import now directly from Rhino, okay? But before you had to export as a step, right? So yeah, it looks like that's quite okay. In any case, I'm going to double check also with the stool1 file that we just had here. So I'm going to open with actually drag and drop. And then I'll just pass the control again back to you, Milad, so you can, yeah. I think that I probably have a, okay, no, looks okay, sorry. Okay, it was still, right, it was still computing the calculation, right. So select the object, double check that it's still a closed polysurface, there you go, close polysurface, file, whoa, close this one, file, export selected to my desktop maybe as a step file. Call it test2, whatever, and click on save. We have a couple of different options here about which exact step format we want to use or step scheme, right? And there you go. Now test2 got saved, and I can just reopen it, or round trip as we call it. There you go, to see if it's okay. Takes a few seconds probably to compute everything, and there you go again, our file, which is now completely closed. One thing that I didn't mention is that if you want to further simplify this, you can use the merge all faces command that will simplify all coplanar faces into one single object or into one single surface actually inside the polysurface. Okay, might take a couple of seconds, but there you go. All the top surface, for instance, is now a single one instead of 4 different quarters. Okay, some other tools that you might need to take into account, probably not in this case, but might be worth mentioning, is that you might want to shrink trimmed surfaces to just get rid of redundant or unused control points on large surfaces when you're using only one small part of the surface. You can do it if you want to just simplify and have a smaller file. And yeah, I think that's pretty much it. I know, Milad, if you want to take over and carry on with the presentation.
For sure, Rodrigo. Thank you very much for this presentation. And again, I think you shared the most relevant tools and procedures to simplify a model for simulation. And guys, this is really 50% of the work. And usually, yeah, it sounds very, very strange, but it's really like this, because just imagine you have a very small hole inside this model. You will never be able to calculate structural behavior until it's closed. Or especially what you showed at the ending, this joining coplanar faces can be very helpful in reducing our work. And I will refer to some of the stuff Rodrigo showed you during the live demo I've prepared right now. And right now I will show you how to set up a simulation for this chair, and therefore let's switch to our web browser. And basically, if you want to access SimScale, just go on simscale.com, and there you can sign up for free here and create a community account. You don't need to give us any credit card information or something like this. The account is free and will stay free. And if you want to use it for commercial purposes, you can also directly schedule a professional demo with one of our sales engineers. However, yes, this is a SimScale workbench in the web browser, and I have for sure prepared a project to make sure we can show it very quickly. So let me first of all show you how to import the geometry. There we have this geometry upload button, and here you can basically just select the file type, and we also support Rhino file format for 1 week now. You can give it a name, for example, chair, and then you just need to open a file. For example, here's a Rhino model, click on Start Upload, and the model will automatically be uploaded to the SimScale platform. And from that point on, all the data is stored in the cloud, and this is massively accelerating our workflow, because we are not limited anymore by our local computing power. So this is a chair model. And now, the first point, we have to create a mesh, a simplified model. And therefore, just click on Create a New Mesh, select the geometry, click on Save, and then you can directly add the mesh operation. And there are different kinds of meshes, and for finite element analysis, we support so-called tet-dominant meshes, which mean you will divide your geometry in a lot of small tetraheders. And you can do both. You can do fully automatic meshing, where you just have to define like a mesh fineness grade and some general settings. But you can also do, if you want, manual meshing to have more control over the element size. And here, let's just do a very simple example. Choose automatic meshing, click on Save. And since this meshing generation process can take up to 5 to 10 minutes, I have prepared this. So this is exactly the same geometry, the same settings, and this is how the final mesh will look like. And if you take a look, it's really a smart algorithm, automatically refining the mesh everywhere we expect to have higher stresses and higher displacement. And so basically this is just one click for you, and then you have your mesh. And once the mesh is created, you can start to set up the simulation. Click on New Simulation, and first of all you have to choose which kind of physics you want to simulate. And in our case, we want to find out what is the maximum load this chair can handle. So let's take a static solid simulation. Click on Create, and then on the left side you can see that everything is prepared automatically. So first of all we have to choose a mesh. Click on Save, and this mesh will be added to our simulation, and you can see it right now here. Then basically we just have to perform 2 steps. The first step is to choose the material we want to use for our analysis. And you can specify every material you want based on the material properties. For our static simulation we can use linear material properties only, but for non-linear static simulations, for sure you can also simulate plastic material behavior or hyperplastic material behavior. And instead of specifying the material behavior based on the Young's modulus and the Poisson ratio, which you can check up in a lot of standard books and tables, we will just import the material from our library, in this case ABS, a quite famous polymer also used in furniture design. Now we apply this material properties to the whole chair, click on save, and the only thing which is missing now is to add so-called boundary conditions. So let's start. We will fix the chair to the ground here, selecting the 3 lower faces and using the type fixed support, so all degrees of freedom are fixed. Oh, one, I forgot this one. And we need to add a load. Therefore we switch to boundary condition loads. Force is fine. And now let's in that direction. And instead of using a fixed value, we can even ramp up the value. So let's say 2000 Newton, which would be 200 kilogram, multiplied with t. And t is later our pseudo time. Don't be confused by that. It will just allow us to test several loading cases in one simulation. Well, that's it. Finally, we just have to choose how many steps we want to do, and we will do 10 steps with this time step length of 0.1, which means we will investigate 10 different load cases from 0 up to 2000 Newton. And that's it. We can just click on save. We can also, if we want, add some result control items. For example, we can calculate automatically the maximum minimum stress inside our chair, and then we just need to create a new simulation and it will be calculated automatically. And again, since this can take up to 10 minutes, I have prepared a project with exactly the same settings which I run in advance. You can see how long it took, 8 minutes, and now let's take a look at the result of the simulation. First of all, if we take a look at the volume calculation, here you can see for different load steps. So this is a load step. This means 100% of the load of 2000 Newton, and this means 0% of the load, so 0 Newton. And here you can see this red graph representing the maximum stress which is occurring inside our model. And just for you to let you know, the yield strength, so this stress where plastic deformation will start, is around 60 megapascal, which is here. So until we have 70% of the load, everything is fine, but if it is higher, we will have plastic deformation inside this chair, which means that in the long term this chair will crack. And this is the first insight we got. So now just with this 5-minute simulation setup, we are able to predict what is the maximum load this chair can handle. And we can also calculate the displacement. And for this maximum load at 70%, we have around 1.5 millimeter of deflection. So now let's take a look also at the 3D simulation results. So we can also take a look at the 3D results as I mentioned. And now this is our chair. This is our simulation step. So 1 is at full load and 0.5 is at half load. And now let's just add a filter, wrap by vector. And now we will wrap the displacement vector, which means that now we're representing the actual deformed shape of the chair. And we will color this not anymore by the displacement, but by the von Mises stress. And now if we activate the legend, you can see it quite clearly. So this color is representing the stress. And now we have a range from 0 to 80 megapascal. And let's change it to, change it. And now everything which is orange or red is a problem. There we have plastic deformation, which means to make sure this chair will resist all the loads in long term, nowhere the stress is allowed to be higher than 6 million Pascal. And here you can see that actually here, and here it starts to crack. And if we go back a step, so if we only have 90% of the load, still there, at 80 still. If we are at 70%, everywhere it's green or blue. And now the simulation will exactly explain us where this high stress is happening and allow us, for example, to improve the design here, for example, here or here, to make sure it won't crack. And we can even animate this result. So just click here on play, and then you can see like how stress distribution is changing for different load states. And even the deformation is considered. So if we change the view like this, for example, you can see how it's deflecting. All right, that was our short live demo, and I see there are a lot of questions. So let's go through it. John Edwardson wants to know if it's possible to simulate composite materials with anisotropic material properties in multiple layers. John, that really depends right now on the problem. We don't support right now anisotropic material properties, but for sure there are ways to model composite materials a different way using some smart workflows. And we have customers which are actually using SimScale to calculate behavior of composite material. And if you're interested in that, I would like to connect you with one of our application engineers. So just write me your email address into the chat and I will send you some information. Then there was another question by Doril, and Doril wants to know if SimScale is also able to simulate firing processes. And this for sure is another kind of analysis. It's computational fluid dynamics, and we talked about it last week, but in general it's possible. And if you want to get a personal demo, just reach out to me by email and I will organize a demo with my colleagues for you. All right, so now let's take a look at two case studies. And what we showed you right now is really just a simple example to make clear how easy and straightforward it is to set up a simulation. And since Rody told me that most of Rhino users are involved in consumer product design, architecture, ship hole design, we just took two examples which are showing how our customers are leveraging simulation. And I hope that this might be an inspiration for you. And the first case study is from one of our customers who is designing kids' bikes. And he wanted to improve and test virtually the durability of these wheels using simulation. So here you can see the two design alternatives he was considering. And as you can imagine, this kid's bike are under heavy load. And you really want to make sure that they don't crack, that they last, and that they're safe. And especially the wheel is something which is very important because it's like taking all the loads and transforming them through the whole bike. And therefore, since this wheel is in contact with the environment, it's very important to make sure that it won't crack. And basically, there are two perspectives. The very first one is that we want to make sure that no of these designs undergoes permanent deformation under the standard loading conditions. Which means that we have to stay below the yield limit of the material for all load cases. And this is like the maximum stress it can resist. And another perspective or another dimension is not the maximum stress, but like stress related to the number of load cycles. If you think about it, there are two ways to destroy something. One is to apply at one time a very, very high load, which will directly destroy the material, and another one is to use a smaller but cyclic load, which will destroy your material or let your material crack on a long term. And we want to investigate both with the help of simulation. And there are different criteria. So for a one-time peak, it should be below 21 megapascal, and for load cycles below 20 megapascal. Here you see the two designs, a 3-spoke wheel and a 5-spoke wheel. For sure the 3-spoke wheel has a lighter weight and therefore is also cheaper to manufacture. So let's first take a look at the two load cases we investigated. One is the radial load, which is mainly applied by the weight of the bike itself and the interaction with the road, and another is the lateral load, which is basically depending on interactions between the wheel and their environment. Just imagine you are hitting something with a kind of angle between the driving axis and the axis of the object, and you will get a lateral load. And basically every kind of load can be represented by a combination of radial and lateral load. And first of all, so for this simulation we apply two loads. First one is a radial load of 35 kilo, 350 Newton, which is on 35 kilo, and here you can see the von Mises stress. And as you remember, we said 21 megapascal. 12 megapascal is the maximum stress for the fatigue limit. And here you can see basically if we have this a 3-spoke design that we have really a fatigue limit everywhere where it's red. So here, but also here, there is a high chance that this design will crack under certain load cycles. And in contrast, if we have 5 spokes, we not only have lower peaks of load and von Mises stress, but also the overall distribution is much lower, and we have much more blue low stress areas. And if we take a look at the lateral force, it's a little bit similar. In total, the difference is not as big as compared to the radial forces. However, if we have 3 spokes, we still have this stress hotspots where we are reaching the fatigue stress limit here at the corner of the spokes. For sure, here the impact of the number of spokes is lower, since the effect of the spokes is much higher if you have this radial loads which is going through the spikes. And finally, there's a second view for the lateral load here, where you can see also like how it's affecting the overall distribution of the load. And again, having 5 spokes makes the whole distribution more smoother, and we not only are reducing the high of the peak, but also the overall stress load inside the design. In total, if we compare two designs, the 5-spoke wheel, for both cases, radial load and lateral load, is fulfilling our design criteria and not reaching the critical von Mises stress for a load cycle. While it's a 3-spoke wheel, we are even reaching the total yield strength at the beginning, which means that, in simple words, the 3-spoke wheel will crack for radial load just because of the low peaks, and in the short term and in kind of long term crack because of the lateral loads, while a design with 4 peaks will not crack for radial or lateral loads, independent if we're talking about a long time load or a short time peak load. And basically this information now helped our customer to improve the product, and they identified 2 options which they further investigated with simulation. One was to increase the ring width for the 3-spoke design, and the other was to use higher grade material to increase stiffness and fatigue limit. And I would like to also introduce you to another demo. Another of our customers is developing snap-fit designs. And I'm quite sure every one of you is owning at least one product, one bag, something where a snap-fit is used. And the good thing about the snap-fit design, that's basically one of the simplest mechanisms to join 2 bodies, and at the same time it's very secure, cheap. And as I mentioned, you will find this kind of snaps at mobile cases, in helmets and toys, in keyboards, basically everywhere. And even if it's so a simple design, it can be very challenging to optimize the snap fits. And therefore, you have to understand how a snap fit is working. So basically, we have two parts. And what we are doing, we are moving one part into the other one. And then through this shape here, the snap, it's banded down. And once it passed this area here, it will snap up again, bend back here, and then it's connected. And whenever we apply tangential load, it will, or compression load makes no difference, it will keep both parts together as long as we release the snap fit by using, for example, by bringing this up again, this blue part. And therefore it's a very, very smart way of joining two bodies, because actually it's adding pre-stress itself. And now when you want to design such a snap fit, a lot of times it's not only about the functionality but also about the design, and you want a nice looking snap fit which is matching to your overall product design and which is also robust enough. And so the first thing our customer did was to compare our simulation results with their experimental results based on data provided by Bayer, the German chemistry company, which is producing a lot of raw materials for snap fits, like polymers. And basically, we wanted to study the stress acting on the two bodies during the mating process, and also obtain the mating and reaction forces which are defining the stiffness of this contact. And so we had these experimental results, and we tested two different simulations and just changed the snap fillet. So this radius here from 0.7 millimeter, which was the initial radius, and we also did run with 0.5 millimeter. And if you see, the results are really matching. So the difference between mating force between simulation experiment is below 2% for both kind of forces, for the mating force during the connection and the deflection force which you need to release the connection. And the small difference we have right now, they are mainly related to the meshing rate. Our customer used a quite coarse mesh for the simulation, and if you increase the refinement of the mesh, it will further converge to the experimental results. And here, for example, you can see three different snap fit designs, which were investigated by our customers. So, and one aim, for example, is also to reduce the stress concentration here at the fillet, because this is the point where most of snap fits in the long term will fail. And especially if you take a look at this long-term load cycles, it's very important to decrease this stress peaks as much as possible. And one way, for example, to achieve this is reducing the snap thickness at the base, and which will reduce the stress concentration, but this will also reduce your mating force drastically. And so this is basically, again, a very good example how simulation can help to find the best compromise in such trade-off situations, like when it comes to optimize a snap fit. So you can see we've reduced the, here you can see, for example, if we increase the thickness at the base, we will have increased stress. If we reduce it, the stress will go down, but the mating force also. And this kind of simulation is now used by our customer to optimize the correct combination of fillet radius and snap thickness individually based on the requirements of the project and the customer. And in the end, this is an example for such an optimization. So here, for example, the stress was reduced by 30% of the snap fit design, while keeping the desired mating and reaction forces. And this stress reduction by 30% can up to double the lifetime of a snap fit. Okay, thank you very much for staying here with us. And I saw we have a lot of questions which I would like to answer now. So Thomas wants to know if we can work with nonlinear analyzers too. Yes, for sure, Thomas. That's not a problem. Just to show you what's the difference. If you want to do such a kind of simulation, you basically just need to change your simulation type from, or here just to change nonlinear to true. Click on Save. And now you can also add other kind of materials. For example, plastic material behavior or hyperelastic material behavior. Doral has another question. He wants, and it's about if it's possible to simulate roof support wood in the underground mine on base of the maximum principal stress. Maybe you can explain your question a little bit more in detail. But basically, SimScale allows as a really wide range of application, and basically even if on the first view it looks like it's not applicable, most of the cases we find a solution which allows our customers to get reliable results for their application. And we can for sure analyze principal stresses and stuff like that. You can just add it during the simulation run. Okay. Seems like all questions were answered during the session. In the case one of your questions was not covered right now, just reach out to us writing an email. Thank you very much for being here with us. It was a big pleasure. I hope you enjoyed it too. And yeah, hopefully, yes, we will become soon part of the SimScale family. Oh, just one thing by Rodrigo. He said that if you have questions, and you can just reach out to him on rhino3d.com using the forum. Guys, thank you very much. Also, Rodrigo, thank you very much. It was a big pleasure to work with you, and we hope you enjoyed it. Have a nice week. See you soon. Bye.